Okay. Okay, to start with, we start for the definition of the curl. So let me write here the curl. Okay. So suppose maybe we start by defining the vector fields. Suppose we have a, let me write maybe here. So let's say we have F, and this will be supposed to be our vector field. Okay, now let me write this F is a vector field on 3-dimension space, and the partial derivative, or let me write partial of P, Q, R all exist. So this assumption, then the curl of F is basically, let me write the definition. So curl F equal del del R del Y minus del Q del Z, and this is in x-axis, plus del P del Z minus del R del X. And how we can come up with this formula I will explain later. This is for J plus, this will be del Q del X minus del P del Y. Okay, so first we start with these definitions. Okay, now to help define what it is, this is, okay, to help out why this is going to be a, why the pattern or the structures look like this for the formula, we can start with, to make it simplified. If we remember the del operator or the nabla, this one, this is we call as a del operator. And we know that if we have the del F, it means that this will be a vector based on all these partials, right? With respect to X for X-axis, Y for Y-axis, and Z, right? And if we just take the operator out, if we just take the del, we could write the del only without the function. This becomes only the dou X. This is on I or X-axis, dou Y for J, and dou Z for K. Okay. So when we operate in terms of some F, this will be dou X of F, or dou F dou X in X-axis, and the same thing here, and also for Z. Okay. And the way we define the curl, we can define by taking the cross product of the del and the vector fields. Okay. So we could perhaps start with, I hope you still remember how to do the cross product. So let's say this is the cross. So basically, because it is in the terms of factor, so I will take the del as the 3-axis, ijk on the top, and then the del will be dou x, dou y, and then dou z. And then this will be the f, q, r. So we can start by taking the determinant for matrix 3 by 3, right? So we can have, this is for I, this will be this and that, right? So dou r, dou y, minus dou p, dou z, multiple with I. And then we have for j, this will be, it should be, for j should be dou r, dou x, and then dou p, dou z, minus, but this is for minus, right? I will exchange this, become positive. So it's much more, so instead we have having the negative part here, I will change this to positive. So this will switch this to, right? So this will be switch out. So that's why we have this is dou p, dou z minus dou r, dou x, okay? Because I want all the positive value outside the brackets. And then the last one is for k. So this and that, right? So that will be dou q, dou x, minus dou p, dou y. My p is not good. Okay. And then k. So I think this is easier definitions to be remembered of. So you can have the del cross f. So that is a curl f. Now, what is actually the curl? So the curl is basically, if we have the rotations, supposed to be rotations. So if we have like, let me give you this. If I have the example, okay, maybe later. Okay, there will be some example, okay, on how the curve will be. For now, let's just take some example first, and then let's see the other definition. So this is curl, okay, curl f, which is the constructions of the del operator cross product with the f, or a factor field. So it's actually, let me just write, maybe just write, although maybe not details, but I will write that the curl factor is measurement how quickly the suppose you have some particles, okay, in the vector fields. Let me write the particle. Move around. Okay, move around the axis. So it means if you have a curl f equals 0 at a point at let's say point, let's say B, or maybe later I will write. There will be some explanation about this. Let me just write this first, okay? Just for introductions. So if you are in class before we move to the notes, you notice that in the graph that I showed you in the beginning, there is rotations, right? So if I change the parameter, the rotation become fast, become slow. So it is the measurement of the curl. Okay? So depends on how the vector field is, we can make the rotations becomes very fast, becomes slow, or even it can be 0 as well. Okay? It can be 0 as well, which means that it is free from rotations, And how it moves is basically depends on the vector fields, okay? The directions, I mean. Okay, so maybe just a quick example how we use the curl. Okay. This is just a quick overview. So if we have this curl f, and this is asking if we have the f, the vector field in xyz. So basically, what we need is we take the curl, and then this is basically the del cross f, and we can make it into a 3x3 determinant. Okay. So I think because we learn matrices in the first half of the lecture, so I hope you are familiar with the determinant. So the del operator will be the dou, the partial, without the function. And then this will be PQR, which is the xz, xyz, and then this is minus y squared. Okay. And basically we are doing the determinant 3x3. Okay. So we can have, this will be starting from the x-axis. We have the dou y of the negative y squared minus dou z. Oh, I think I need more space. Let me. Okay, hopefully this is enough. So dou z of the xyz. Okay, and then this is for I. And then I will just directly compute the determinant. So for j is, let me just minus this. Okay. Or if you want to write the formula before, you could do directly, but I think I prefer this determinant because I believe this will be more easier to compute, okay, rather than taking the formula and maybe memorize the formula. Maybe that using determinant will be easier. So j will be the dou x of negative y squared. I think this will be 0. And then minus dou z of the xz. And I will just keep that as a minus in here because we don't really much care. So at least if we could determine, then it's good. Let me make it smaller, this part, and smaller also that one. And then plus, this will be for k. This is dou x, xyz, and minus dou y, xz, which is I think 0, right? So one by one we can take down. So this is negative 2y. This will be z is xy. And this will be I minus, this will be 0. This will be minus x. This is j plus, oh, I forgot the k. This will be yz minus 0, right? Minus 0. So this is k. So we have negative 2y, or maybe let me factor out negative y, 2 plus x, this is I, plus x j plus yz k. Okay. And this will be the curl f. The interesting theorem about the curl also, if we have, for example, we have the second partial derivative. We can have a second partial derivative. So if we curl the del f, which means that this will be the del cross product with the del of f. Okay. Or perhaps let me write the f as in just a function, normal function like that. And then we can make the determinant 3 by 3. This will be the operator. And the last row will be the del f. So dou x of f, so dou f dou y, dou f dou z. Okay. Now when we have the operator for partial and then multiply with the other partial, it will be the second order, right? It will be the second derivative. So this will be equal. So let me write this as, for the y-axis, we have dou y and then dou f dou z. So we have dou y dou z. Okay. So which means this is partial from f. We take the z first and then y, right? This actually means dou y, but inside this we have dou z, right? That's what it means. Okay, I will just write that to help you relate. And then minus, the other one will be dou z of, let me just write this, dou f, dou z, dou y. Okay, this is for I. I think I need to make it smaller. Okay. Next is we take minus of, or I will write as a plus, and then I will, or maybe just minus. For j will be dou x and dou f dou z, right? And then minus dou z dou x. Okay. This is for j. And then plus. For k axis, this will be dou x dou y minus dou y dou x, right? Okay. Now if we look back to the definitions of the second partials, remember that in the calculus 2 we defined that no matter the order, the result will be the same, right? If we partial with x and then partial with y, if we compare to the partial y and then partial x with the same functions, both will be resulting the same, right? So this two is the same, right? It's the same. So all these terms will turn out to be 0. Okay. Remember that in partial derivative, with the Clairaut's theorem, the partial xy will be partial yx is equal. Okay. Which means that this will be resulting a0. We call this is the Clairaut's theorem. Okay, so every function for 3 variables that has the secondary partials, the second order partial derivatives, the curl of the del f, it will always 0. Okay. And this is a shortcut to find the conservative vector field. Okay, so instead taking out the partials and equaling with the other partials, for example, you have usually you have this method, right, to find the conservative or not. If this is equal, the partial equal, it's conservative. But now we can use this method to check the conservative or not. So if we know that the vector field is basically the del of f, the small f is a potential function, then if the vector field is conservative, then the curl of the vector field is 0, or the curl of the del f is 0. Okay. So you can also check the conservative of a vector field using this curl. Okay, just checking the curl del of the potential functions, it should equal into 0. So you could immediately get the value if you are taking the curl, which means you are taking this vector or the partials compute, and if they are equal. So I think it's also proving that if this is true equal, then when you are doing curl, this too will be subtracted to 0, right? Because it's conservative. So I think it's adding some additional context to the conservative. Okay. So let me just I have another definition here, and it's still the same topics, the conservativity. So we have the vector field, and if we would like to check whether it's conservative or not, we could check the curl f. Okay, so we could check the curl f or the del and then cross f. And if this is not 0, then this is not conservative. If it is 0, then it will be conservative. So if we check this, then we could check this is I, J, K. So this will be dou x, dou y, dou z. So this is x, z, x, y, z, and minus y squared, right? And then take the cross product. This will be dou y. I think we have done this, right? Is this the same? Same? Oh, the same. So I think I will just copy this. Okay. Since this is the same example, I thought it is different. This is for reference. So the curl f, we have the curl f as a factor, which means the curl f is not 0, which means the f is not conservative. Now this is pretty useful if you have 3 variables. Okay? If you have 3 variables, but if you have only 2 variables, I think you could just using the independence path method that we have been through last week. Right? So this is giving you another theorem, but I think the theorem, it will be very intuitive as long as you have a consistency of all the definitions. Okay, so all the theorem is all related. And so that the curl could give you some additional information, especially determine whether the vector field conservative or not. Okay. Let me give you example here. I think example I can write here This will be over, I will move over there. Also this picture, I can move over there first. Okay, we can focus on this example now. So if you have these three variables function or vector field function, then we could take the curl to show whether it is the vector field is conservative or not. So we could take the del cross f. So take the I, j, k. This is dodo x. I think if you are getting familiar with the finding this determinant, you are able to do the calculations faster and no need to write this determinant structure. But I think if you still need to write, you can just write the determinant like this. Okay, I will write here and 3x y squared z squared. Okay, I think I will write down here that I start with the I. This will be dou y of 3xy squared z squared, and then minus dou z of 2xyz cubed, close bracket I think I will move a little bit to the left. This will be minus dou x of 3xy squared z squared minus dou z and then y squared z cubed. This is j. I think still need to make it to the right side. Maybe make it a little bit smaller. And then plus, for k, this will be dou x and 2x yz cubed, and then minus dou y squared z cubed, and this is k. So this is curl f. So curl f is, we can compute partial with respect to y. This will be 6x y z squared, and then this will be 6xy z squared. Okay, and this will be 3y squared z squared minus 3y squared z squared. I think this will be all 0, I think, and plus this will be 2yz cubed. Yeah, and this will be minus 2yz cubed as well. So this will be 0. So which means that f is conservative. The second part of the questions is the same questions from the previous, the line integrals, or the finding the independence of the path. So if we want to find the potential function f, then we could write partial integrations. So for example, we have here the partial x is y squared z cubed from here, right? Partial y is 2xy z cubed, and partial z is 3xy squared z squared. You can basically pick one of them and then take the partial integrations. But remember, since this is 3 variables, the constant you're expecting is a function two variables. If you have if the vector field is two variables, if you integrate, you will get the function of one variable, right? But if this is three, then when you integrate, you will have function of two variables, right? in the constant. So if we take this partial x, okay, we take the integrating with respect to x. So let's say this is y squared z cubed and then dx. We are going to have x y squared z cubed, and then the constant will have the, let's say we have g, function g, but this will be two variable. Okay. So we have two layers to solve. Okay, we need to solve for this g, and basically we are going to compare the partials. Okay, we are going to compare the partials. So this is our proposal for f. So this is supposed to be our functions. So we are going to take the partial either to z or y for the whole functions. Let's say we are going to partial with y. Okay. So we take this, let me write maybe a little bit down here. So take this as with y. Okay, so we get the partial y. So we have, this is partial y will be 2xy z cubed. Okay, this is in line with our initial or origin formula, but the g will be having g with partially y, okay, partial derived with y of this yz. And since there are nothing on the initial partial y, there is nothing, so we can confirm that this will be 0, right? This will be 0. So we can let this is equal 0, right? From our initial origin structure. So if we integrate this, integrate with respect to y, then this will be a function of z, right? Function of z. Because if we derive z without y, there will be 0, right? So we can imagine this for this g as a function of z. Let's say h. Okay. And then we can compare to the partial z. So again, we can extend this g, this h, we can extend to this. And then doing the same thing, but we are taking partial derivative with z. And then compare with this. Okay. So perhaps the questions will be more, will having more complexity if it has something else here, right? Additional information. Like you will have the different integrations. But since there's nothing, so we can focus that all the additional will be 0. So it's easier to solve. Right? So I think we can change or substitute this h to this, and then doing the same thing, we take let's say this is the function. So we have the hz, and then we take the partial with respect to z. So we are going to have the partial z, which is 3 xy squared z squared plus the h prime z. But since there is nothing, so we could also say that the h prime of z is 0. So the h of z will be a constant. So finally, let me write the final conclusion for the functions. F x y z will be equal x y squared z cubed plus a, let's say a constant k. Or maybe if you want to write c, it's okay, but I will write k. So k is a constant. Okay. So basically, the curl will be emphasized, clearly emphasized, if your vector field has a kind of rotations, and somehow we could measure, perhaps like in fluids, if you maybe learning some fluids, you will basically if you model the fluids, you are going to see the curl, and also later we are going to learn about the divergence. So the curl, as the name suggests, that's going to be curly. It's going to be rotate. Okay, so it's basically associated with rotations. Okay, so if we look at here, just a quick review here. So the curl, based on the right-hand rule, because we have the cross product. Remember the cross product using the right-hand rule. Using the so let me write here. So curl associated with rotations. So if curl f is 0 at some point p, then if we imagine this as a fluid, then the fluid is free from rotations at p. We call this irrotational. If we compare these two pictures, we'll see that based on the calculation on the curl, you see the below part, the curl on the left is not 0, on the right is 0. If you see from the picture what is the difference The difference is no matter what the point on the right side, it will not be affected by the curl. But the left side, if you see, imagine we have these 2 points P1 and P2. So the P1, it would rotate counterclockwise. So here, can we rotate counterclockwise? Rotate it. And it will rotate about the its axis, okay? Okay, we are going to have a break for a while. Okay, and let's continue. So if you look at this picture, if you compare point P1 and P2, since the curl is based on the cross product, and the cross product is based on the using the right hand rule for the directions. So if we have the clockwise rotations, so if you use the right hand rule, this will come out, if that is positive x and y, so this will be going forward for the z-axis positive, right? Or in vector, it will be going to be positive k, right? So direction will be in, so how to write that? The curl is in a positive k direction. Okay, for P1. For P2, if you see the point, it is rotating clockwise. So if we take using the right hand rule, it's going inside, right? It's going inside. So this part here, so it will be clockwise rotated, which means that the curl is in negative k direction. Okay. And if we compare to the right picture, the right figure, the point P, it doesn't have any relation with the rotation because it doesn't connect to any rotation movement. So we call this is irrotational, or if you see the curl, it's zero. If we compute the curl, it's zero. So you could imagine in terms of visuals, if you can make into graph. I think the easier way to graph this is to look at the xy plane. So it's actually 3 variables, but to look at how they are rotating, we could project to xy plane and then see how it's rotating, whether it's going to the positive k direction or negative k directions. Okay. So here for the, I think we can write for this one, the curl f is 0, which means it doesn't rotate about its axis. Okay, so this is curl. Okay, the counterpart of the curl we call as divergence. So let me open a new slides to get through the definition first. So this is all about curl. Okay. So the next part is the divergence. So let me get some terms. So we have a vector field F. Let's say this is P, Q, and R. So we have this PQR. This is a vector field on 3-dimension space. And assume the partial exists. We have divergence of f or sometimes we write as div and then f. This will be all these partials, and then we add all these partials. Or if you want to see the more clear, maybe that is better. And remember that the div f, based on the equation given, this will be resulting in scalar field. So this is a scalar field, not a vector. So then, by taking this into the vector operations, so because we have the plus, the additional product for the partials, so we can, if we have the del as our operator, then the div f we could have, so if the del is dodo x I dodo y j plus dodo z of k, then the div f can be seen as the del, and then we dot with the f, okay? So that we have a scalar as a result of this dot product. So we have this. Okay, maybe giving some application on a quick example. So suppose that we have a vector field f. This is our vector. This is, I think, the same example as the previous one for the curl. So let me just get through for the div, divergence of f. This will be del dot f. So dodo x of the xz plus dodo y of xyz and plus dodo z of negative y squared. This will be 0, and this will be z. This will be xz. So this is the div of f. Okay, now if we combine, if we have the curl and then also div, so if we, should be v, sorry, should be v. So if we want to, for example, if we want to take so if we have the, suppose we have the p, q, r, each one of them in each axis x, y, z. This is a vector field. So we know the curl of f. How about if we want to get the divergence of the curl f? Okay, so which means based on the operations, we are going to compute the curl, which is the del cross f, and then the result will be dot product with another del. So this will be del dot product with the del cross f. Okay, we have done the del cross f, so I will just move the result and then take the dot product of it. So the del operator will be dou x, and this will be the curl result. So dou r dou y minus dou q dou z. This is for the y-axis or the x, and plus dou y of the dou p dou z minus dou r dou x, and the same thing with z. This will be dou q dou x Okay, now we have the second partials, okay, because we have the partial inside from the curl, and then we take another partials and then add all the terms, right? So basically we have dou x, or maybe let me write the dou squared r, dou x dou y, right? And then dou squared q dou x dou z plus dou squared p dou y dou z, and then minus dou squared r dou y dou x And then again, because this is a second partials, and the order in second partials, no matter from x or y, if you have the same respectable derivatives, then it will be the same. So for example, we have r dx dy, and then this is dy dx. There is basically the same, right? The same results. Also, we have the dou x dou z, and also for this dy dz, or dou z dou y. So they are going to subtract it, and basically because they are equal, we are going to have this will be 0. Okay. So the terms, terms cancel in pairs by the Clairaut's theorems. The same with the previous example. When you have the second partial derivative, the partial xy will be equal to partial yx. So it will be 0. So the div curl f will be equal to 0. This is a quick example on this theorem. If you see the example 5 here, we have the same vector field like the previous example. So showing that this f cannot be written as the curl of another vector field, such as the f is not equal to curl g for any vector field g. So because we know that the div f from our previous example is z plus xy, so since this is z equal z plus xz, right? Xz. So therefore, div f is not 0. if f is equal to the curl G, okay, then the diff f equal diff curl G equals 0, but it is not, right? So right, it is contradicts that the diff f is z plus xz, or diff f is not 0. So therefore f is not the curl of another vector. Okay. Another way to understand this part, if you have the diff f equals 0, we can say that the f is incompressible. Okay? Like maybe we can imagine like a fluid or gas. Like if you have a fluid flow, we can say that the if the f, the vector field, is velocity, let's say velocity of fluid, then diff f, or let me write with red color. So diff f of xyz, it will represent the net rate of change with respect to the time of mass of fluid, which going to be flowing from point, let's say any point in the xyz per unit volume. Or we could see that the diff f is the it will measure the tendency of the fluid to diverge from point anywhere in the xyz. Thus the name is divergence. Okay. Okay. Now to get you a glimpse on how this works, perhaps if we could see this picture. We have these two pictures. Let's focus on the left side. Okay, the left side is having the diff f is a we have some value. Okay? We have some value here, which is 2x plus 1 for the diff f. So what does it mean for the 2x plus 1? So if we could perhaps pinpoint any p, for example, in this p1 here, you'll see that in this point, we could see that nearby this point P1, we have the a direction that is coming out, which the value itself is very small value. Okay? Compare with, perhaps we have this, which is a little bit far from P1, it has the longer or a larger value, which means that this perhaps, because the shorter one is near the P1, we could see that this could be a negative value. So P1 will be a, or let me write, diff f at P1 is negative. But if we compare to the P2, if you look at the P2, now it is the one that is going out is larger than the one that is coming to the point. So the net rate, so it's actually the one that is going outside minus the one that is going inside. So this will be a positive value. Okay, the one on the right side, if we imagine that, okay, if we look at the when we have diff f, if we look here, the one that is coming and then the one is going out, the value is the same, the length of the directions. So this P, for everywhere you put that point, it will be 0. So I will write here the diff f so the vectors that start and end near any point P are about the same length. But perhaps we need to make this is again, the picture is approximations. Like you can change the parameters, so maybe you can make the units maybe very small, like smaller direction. But I believe if we just look at the point in the macro view, you can see the differences. And I think also we can imagine the where is it? We can if we have, for example, let me give you another point of view. Like we have the point P, and then perhaps the vector field is coming out like this. Okay. We say this is diff f is positive, right? Because it's coming out. Okay. Maybe the picture below. I should start with the top one. Okay. The picture below is more. I think a little bit more. Need more visualizations. But here we see that because it's coming outside, no one that is going inside, it is precisely to be positive. If we compare with if we put the direction inwards, suppose that this green arrow is the vector field. We call this a negative. The conditions, we say the P on the first one is a source. The second one, we say the P is a sink. Sink like in when you wash your hands, it goes into sink, right? The water goes to the center, right? So we call that the point P is a sink. So when you see any divergence that is going to be negative, that will be the sink. And basically, because the diff f is a scalar equations or scalar field, so based on the point you put, like for example here, this could be like this is positive or this is negative. And when you get the diff 0, this is you can write this is incompressible. Incompressible. And sometimes in one vector field we have either there's one we call the source and the other one we call the sink, and basically the diff will be the net rate of change on the outward and inward directions of the vector field. Okay. So you can use this for perhaps like in the fluid or in the mechanics of fluids, or perhaps in the electromagnetic field. This is also the term will be very similar with perhaps different interpretations, but the same definitions and the same tools. So for today we've done the curl and divergence. I think there is one more notes within this a curl and divergence. I think we can get into that. Okay, so another part of before the next one, I need to come out for just one notes, because we have the previous curl. In the previous curl, we have when we have the curl. Where is it? We have the curl del f. Okay, let's do the same thing with the divergence. Okay, so the divergence. Where is it? Oh, I think I will add another one here. So if we compute the diff of the del f, so the operator will be the del and then dot of the del f, and del f is a partial x, y, and z, right? So basically, because del and del will be multiplied, the operator will becomes secondary partials, or the second partial derivative. So this will be that for x, and then this will be, and again this will be resulting in the scalar field. So the del squared is basically del dot del. Okay. So sometimes we could rewrite this as a del squared f. So the del squared will be the del dot del, which is secondary partials or second derivative of the functions. And if this is equal 0, this is, we call it Laplace equations. which if we have time, we could get into more of this, but if no time, then we skip that. We can apply to the vector field as well. So if f is pi plus qj plus rk, then we could take the operator of the del squared f as the del squared p plus del squared q plus del squared r. So there is another differential operators. We call this del squared as a Laplace operator. Okay. Okay, now one more thing to end the lecture today is the vector form of Green theorem. So we start by taking what we know from the line integral. So suppose that we have a vector field f. Let's say we have two variables. So we have p, q. And if we take the line integral, imagine this is a closed curve for the curve C. So we take the f dot dr. It's basically taking the line integral p dx plus q dy, right? And if we write the curl for the two variables, we are going to let the r equals 0. Okay, so if we take the curl r, or the curl f, sorry, we still taking this as a 3-dimension with r being 0. So this will be stating the same method. This is p, q, and this is 0. Okay, so we are going to have the dou q dou x minus dou p dou y. And this will be k. Okay, the other part will be taking as 0, right? And will be subtracted. So if we take the curl f and then dot with k, so if we take this dot with k, and the k will be removed, right? So now we can write the line integral based on the terms in the curl that we've done. So curl f dot k. So this expression, it gives you the idea for the so line integral express or this is line integral of the tangent component of f along the curve C, as the double integral of vertical component, which is the k, okay, the z-axis of curl f over region D enclosed by the curve C. Okay. Now suppose that we have some, if we could imagine, I forgot to pick the picture here, so let me just draw for you. Suppose we have the closed curve. Let's say this is our closed curve. Okay, and then this is D, and we have, suppose that we have some R, and let's define within this point. This is the RT, and maybe this is not really good. Maybe that is okay. So this is the tangent vector, or the unit tangent vector. If you remember, this is T of T, and the one that is going to be orthogonal, we call as the normal, or N. So this is RT. Okay, maybe not clear. Okay. Suppose that we have RT is, let's say we have parametric, and let's say we have parameter from A to B. And if you remember, the tangent unit vector is basically the derivative of each axis divided with the magnitude of the R prime plus Y prime T. Okay. And we can verify that the normal vector will be Y prime minus the X prime okay. So then if we take the line integral for the f dot n with respect to s as the is the arc length. Then this will be integral from a to b f dot n, and we can write ds. So f dot n in terms of t, and then multiply with the magnitude of the r prime t, and then dt. Now taking the f dot n, this will be based on the pq vector field. So we have still the integration from a to b, and we are going to change the inside of the integrations. We have p, but now we have the changing the xy point with the parametric. So this will be p of x of t, y of t, and then multiply with the y prime t. Basically, this is the n from this one here. And then divide with magnitude of r prime. And then minus the q. Q, exchange the x with the parametric, and then x prime t. Oh, I need more space. Okay, and then this will be r prime t. Multiply with the magnitude here, which will cancel out. And we can simplify this. It becomes very simple and easy to follow. This one becomes p x of t, y of t. This is y prime t dt, and then minus q x prime t, and then dt. Which then we can separate this. And getting back to the line integral, we move back to the line integral and say that this will be basically the y prime t. We can convert back to using the chain rule in dy. So this will be p dy minus q dx. This will equal with the Green theorem using the double integral. This is plus, sorry. P dou y, because this is p dy minus q dx, so this will be my plus. And then this is dA. Or, in other words, that the line integral for f dot n with respect to ds, this will equal to double integral. This is basically the diff. So diff divergence f, or maybe not, in xy of dA. This is d. So this is diff f, right? So we could see that the line integral of the normal component so line integral of normal component f along the curve C is equal to double integral of divergence f. Over over D, okay, which is enclosed by the curve C. Okay. Okay, so I think I will just mention the important part is here. So this is especially if you have a clear vector functions and you have the in terms of parametric, and then you can clearly see the normal component, or you can make out the normal from the R. You can make out the n. Then basically the line integral of this f dot n will be the divergence of f. So done the curl and divergence. Okay, so the next part, which is for next week, we can start to have the introduction of the surface integrals, or perhaps we can evaluate I think the curl and the divergence, as long as you know how to cross product and the dot product, you could basically solve the most of the problems. So we can start the surface integrals, and after that, I think the last part will be the Stokes theorem. Okay. I believe within 2 weeks or so we can finish, and yeah, I think. Do you think if we finish early, we can have a early final exam, or do you want to maybe? Because I believe you have another final exam as well, right? I mean, to help you to arrange not to close schedule with the other courses. Well, it depends on you. Do you think it's helpful or not?